All right. So we have been looking into the AC analysis of amplifiers. And of course, your homework 5 deals with AC analysis. So if you have questions on how to solve homework 5, this is something we're going to learn in today's lecture and on Monday's lecture. Yeah. Just a reminder that homework 5 deadline will be next Friday instead of Monday because we are still covering the concepts on how to find out the gain of an amplifier. And remember, the most important thing is that whenever we are talking about gain of an amplifier, we are talking about AC gain. So in the problems, if you, let's say, let's see if I can download one of the homework problems. All right. So this was something similar to the homework problem, right? So you'll see some sort of a network like this. Remember that in many cases in the homework problems, let's say your drain voltage is given over here, or maybe the gate voltage is given. So you calculate the gate voltage by looking at the ratio of RG1 and RG2, right? You can calculate the VD if you know the current passing through this path, and if you know the value of RD, you'll know what would be the voltage value VD. When you're talking about AC, all those the values of the voltages, for example, what is the drain voltage, what is the gate voltage over here, those are all DC quantities, right? Because your VDD is a DC quantity, your ground is a DC quantity. So the voltage of gate VG1 that you get over here by calculating the ratio of RG1 and RG2, that will also be a DC quantity. Those are not AC quantities, right? But when you talk about gain, we'll be talking about AC quantities, not DC quantities. So homework 5 is completely different from homework 4. Homework 4 is only DC analysis. Homework 5 is only AC analysis. Why we can do both? That's because of the superposition principle, that you can consider the DC voltages separately and you can consider the AC voltages separately, and things will work out because it's superposition of voltages, right? So when you're doing DC analysis, that's separate from doing AC analysis. And when you're solving homework 5, which is AC analysis, don't consider the DC voltages. So for example, the drain voltage divided by gate voltage, the DC drain voltage divided by the DC gate voltage is not the gain. The AC output voltage divided by the AC input voltage will be the gain. And we'll look at what would be those voltages and what is the difference between those in today's lecture as well as on Monday's lecture. Okay, but just a heads up, please don't consider the ratio of DC voltages as the gain, because gain is the ratio of AC voltage at the output divided by AC voltage at the input. All right, so let's continue with the discussion that we were having in the last lecture. We saw that the gain or the AC gain of an amplifier will be of the form of some GM, capital GM times capital R equivalent. What is capital GM? The capital GM would be the transconductance of the circuit, of the entire circuit that you're given in the problem. Of course, the MOSFET will have a particular transconductance, and that is generally given by lowercase gm, right? Lowercase gm is the MOSFET's transconductance, whereas this uppercase gm will represent this as the transconductance of the overall system. Again, this is analogous to the fact that when you are solving homework 2 or homework 3, your op-amp always has infinite input impedance, but the overall circuit may not have infinite input impedance, right? Similarly, the MOSFET has a transconductance of lowercase gm, but the overall circuit may not have a transconductance of lowercase gm. It could be something else, and that is represented by this uppercase gm. Okay. But the overall gain formula will be some transconductance, the overall circuit's transconductance multiplied with the overall circuit's equivalent output resistance. That would always be true. Okay. And we are now trying to find out what would be those effective GM and effective R equivalent of the overall circuit, and not for the MOSFET itself. Because for the MOSFET, it's very well known. Right? Okay, so this was the first example that we had taken a look at in the last lecture, in the last part of last lecture. So if you have a MOSFET, you know that the small signal, the AC small signal model of the MOSFET might look something like this on the right hand side. So you have a VGS, a gate to source voltage. GM times that VGS will give you the output current of the MOSFET. Okay. So you have this MOSFET, the AC equivalent model or the small signal equivalent of the model is on the right hand side, and you have this VGS, which is the gate to source voltage of the MOSFET, And Gm times VGS will give you the current going through that MOSFET. Now, what's the catch here? What the main caveat in this particular circuit is that you have a source resistance at this point. Right? And the current that is going through the MOSFET, the AC current, is not given. Right? Homework 4, the DC currents were given. The DC current, from the DC current, you found out V overdrive, then you found out VGS, and so on. But the AC current will be a function of the AC voltage, right? AC current cannot be a given AC current. If you provide a larger AC voltage at the input, which is VG, you'll get a larger AC current at the output because AC current is Gm times VGS. So it's dependent on the input AC voltage. So that's the biggest difference between the ID in your homework 4 and this lowercase ID that we are learning now. Homework 4, the ID that you considered was, let's see if I can go back to some of those. Okay, this is homework 5. Let's see homework 4 similar problems. So for homework 4, this ID that was given was for biasing. Remember, DC analysis is only for biasing, only for you to figure out that the MOSFET is in the correct operating region, which is the saturation region. After that, everything we do is the AC analysis. So DC analysis and AC analysis are completely separate things. ID, this uppercase ID that is given here is the biasing current, that there will be a 2 milliampere DC current, even if you don't apply any AC voltage at the input. Even if you do not apply any AC voltage at the input, the DC current through the MOSFET will be equal to 2 milliampere. That's what it says in homework 4. Now, what we are learning now is if you apply a AC voltage, once you have made sure that the transistor is in the correct operating region, the transistor is in saturation, after that you will apply an AC voltage at the input. And if you apply this AC voltage at the input, you'll see an AC current at the output, which is different from the DC current that we talked about in homework 4. Questions?
So that it has in the active region when there's no signal?
Exactly. So the biasing happens irrespective, the biasing needs to be done irrespective of whether there is a AC voltage or not. Because this is just DC. You see that in this circuit, there is no AC potential. There is no AC voltage, there is no AC current. Here, you're just trying to figure out that whether the transistor is in the correct operating region or not. That's all you did in homework 4, right? You didn't do anything else apart from finding out the transistor is in saturation region and what would be the currents, what would be the voltages, DC currents and DC voltages to make sure that the transistor is in saturation. Part B was changing the RD resistance so that you can figure out what is the largest value of RD for which the FET still stays in the saturation region. Again, everything related to DC. Now, your question is, the gate was connected to ground in this case. And remember that that's a DC voltage, right? Now, Vs was minus 1.5 volt, as we had figured out from this particular problem, which is solved in the last class. And that is because VDD was plus 7, VSS was minus 7. So in between this point could be somewhere in between plus 7 and minus 7. We figured out that this will be minus 1.5. If gate is 0, source is minus 1.5, VGS, the DC value of VGS is going to be 1.5 volts. And that VGS minus VT was given to be 1.1. So VGS minus VT, which is V overdrive, that is larger than 0, which means that the transistor is on. And of course, the VDS was also higher than V overdrive, which meant the transistor is in saturation. That's all we did there. And we stopped. Now, what did we achieve there? And we wanted to use the transistor as an amplifier. We did not achieve that because we never applied an AC voltage at the input. We never applied an AC current at the input. We did nothing like that, right? So now we are going to learn, once the transistor is in the saturation region, if you apply an AC voltage or AC current at the input, what would happen? Okay. All right. And for that, let's go back over here. So for example, here you are applying that AC voltage at the input. Again, the assumption is that you already have biased the transistor in the saturation region. Okay, we're not talking about biasing anymore. We'll just assume that you know how to do biasing because all of you have solved homework 4. Okay. So here, if you have this VG at the input, this is an AC voltage. The AC output current, which is GM times VGS, is dependent on VG. That AC output current is not fixed. It's continuously changing because VG, the input voltage, is continuously changing. DC does not change. DC is a fixed voltage. And that's why the DC current with which you biased in the previous problem, so you had ID equal to 2 milliampere. That's a fixed current. Now, on top of that fixed current, you will have a small fluctuations. Remember that any AC is basically on top of a DC. So that, let's say the 2 milliampere output current is basically this DC potential. So that is 2 milliampere of output AC current. On top of that 2 milliampere output AC current, you will have a fluctuation which is denoted by this lowercase ID over here. And that lowercase ID is a function of the lowercase VGS, which is the AC input voltage at the gate. Okay? Or between the gate and the source, effectively. And GM is the quantity, the transconductance quantity, which relates your VGS with your output ID. And this is also an AC quantity because you want to relate your input AC voltage with your output AC current. That's what the job of GM is. All right. So with that premise in mind, what is missing here? Right? So the problem or the caveat here is that at the source, you have a resistance. And because of that, you do not know what is going to be the source voltage. So this is kind of unknown. Let's say this is unknown. Of course, we can find this out. But the caveat is that at the beginning of the problem, this is unknown. Because there would be a voltage drop across RS and the source voltage will be unknown. The gate voltage is known. The gate voltage is, let's say, whatever voltage you're applying at the gate. But the source is unknown, and that is why VGS becomes unknown. The gate to source voltage, which is VG minus VS, that becomes unknown. So GM times VGS will also become unknown, right? But is it really unknown? Because there is a dependence here. For example, this ID output current is GM times VGS. That same ID output current flows through this RS resistance and goes to ground, right? Because the ID is the current that is flowing in the drain. You know that there cannot be any current flowing into the gate or out of the gate. So all the current that is flowing into the drain has to come out of the source, and that will flow through this RS resistance. So the AC voltage VS at the top terminal of RS, that is going to be ID times RS. Now ID is GM times VGS times RS, that's going to be your VS. Now you can write your VGS as VG minus VS, and this is your VS, GM times VGS times RS. This is what you found out here. So you're just putting that value over here, VG minus VS. So you get VGS on the left side of the equation. You also have VGS on the right side of the equation. Take all of that to the same side, let's say the left side of the equation. You get VGS times 1 plus GMRS, that is equal to VG. Or you can write VGS as VG divided by 1 plus GMRS. Now, what is your ID? ID is GM times VGS. So you just expand your VGS as you found out over here. So that this will become GM divided by 1 plus GMRS times VG. So if you're applying this gate voltage, which is an AC voltage over here, if you have this source resistance, then the output current, the ID current, is going to be GM times VG divided by 1 plus GMRS. So originally in this particular, let's say the small signal model of the MOSFET, you know that the ID current is GM times VGS. But for this whole circuit, when you have a source resistance connected to it, the ID current is not GM times VG. It's GM divided by 1 plus GMRS times VG. That is the effect of this source resistance. If the source resistance had been 0, if you had shorted this, then of course this GMRS will become 0 and you will have GM times VG, which is the original concept that you already learned, that the output current is going to be GM times the input voltage. And if this is shorted, the source resistance becomes 0. And that is why VGS becomes equal to VG. And that is the reason why your ID will be GM times VGS, which will be equal to GM times VG as well. Okay. But because the RS is present, the source resistance is present, effectively the GM gets degenerated or degraded. And that is what we meant by the capital GM in the previous page, that you want to represent your gain as capital GM, the effective GM of the circuit, multiplied with the effective R out of the circuit, effective output resistance or equivalent output resistance for the circuit, right? So this GM or the effective GM of the circuit in this case, with this degeneration resistance connected at the source, is going to be GM divided by 1 plus GMRS. So it's degraded, the GM is reduced because 1 plus GMRS is going to be higher than 1. GM, and these are all positive quantities, GM, RS, everything is positive. So 1 plus GMRS is always higher than 1. Denominator is higher than 1. That means your value of GM is getting degraded. Effective GM is lower than the lowercase GM. Okay? And that's why this is called a degeneration resistance. Now the bigger question is, if it is degenerating the GM, why do we use it in the first place? Right? Why would you ever use something like this if your GM is reducing, if your transconductance is reducing? Because as you found out, again, if I go back to the previous page, that your gain, AC gain, is going to be a multiplication of GM and R. So if your GM reduces, your gain reduces. So in this case, with degeneration, your gain is actually reducing. Why would you want that as a designer? The reason is that this will give you better stability in the circuit in terms of the gain. Why? Remember that this is a MOSFET, and MOSFETs can have process variation. That everyone, so for example, you buy a MOSFET from the market and you buy a MOSFET from the market, that can have different threshold voltages. Even though in the data sheet, they might say that the threshold voltage of the MOSFET is 0.7 volts, you might see 0.65 and he might see 0.75. Right? That's always possible. Right? And that is called the process variation or the manufacturing variation. Now, if you just did not have this source resistance over here, what would happen to the current through the MOSFET? Your gate voltage is, let's say, whatever voltage you're providing over here. Your source is grounded to ground, so VGS will be equal to the gate voltage. Now, in terms of the DC biasing, again, if we go back to homework 4 for a moment, in terms of the DC biasing, what is the DC current? ID is equal to K over 2 times VGS minus VT whole square in the saturation region, right? So K over 2 times VGS minus VT whole squared. The problem here is that you have this VT term, the threshold voltage term. And if your threshold voltage is different from his threshold voltage, you'll get a different DC biasing point than what he will be getting. Just because you had nothing to do with it. It's just because the MOSFET that you bought has a different threshold voltage. Now, in this case, what will happen if you have this source resistance is that what will be the effect of this VT going up or going down? Let's say my VT goes up. I replace this transistor, I replace this with something else where my VT is larger. If VT is larger, VGS minus VT is smaller, which means that my ID current will be small. If my ID current is going to be smaller, that is basically the current flowing through the MOSFET. If I did not have the resistance over here, whatever VT my transistor had will determine what the ID current that I'll be having. But if I have this source resistance, let me clear this. If I have this source resistance, the advantage that I'll get is that, let's say my VT is higher than what I expect, which means that my ID will be lower than what I expect, right? If my VT is high, VT is, in the problem, it was given 1.1 volt, but the actual MOSFET might give you 1.2 volts. And in that case, your ID will be lower. If your ID is lower, the voltage drop across RS will be lower. If the voltage drop across RS is lower, then the source voltage over here goes down, it will become lower. If source voltage is lower, VGS becomes higher, right? Because VGS is gate voltage minus source voltage. If source voltage goes down, VGS goes up for the same VG. So what did we get here? This is very interesting, that if my VT went up, if I have this source resistance connected here, my VGS will also go up. And that will compensate of any kind of fluctuation in the threshold voltage. Question? It will almost equally compensate. Yeah. Because let's say you start with a particular amount of ID current, then your VT is, let's say, dynamically VT is changing because of temperature. Let's say there was a temperature change, and because of that VT changed. What would happen if VT went high? in that case, your VGS will also go high by the same amount and your ID current will remain same, right? So that is the advantage of putting this source resistance, even though it will degenerate your gain. So the need for this source resistance comes because you need biasing. And if you can bias it with a fixed amount of current, it's always better because you know that your current is going to be fixed all the time. All right. We'll also learn a scenario when we'll say that, okay, I can bias, I can make a stable bias by having this RS, but my gain will not degenerate. It's possible to do that. I'll teach you how, but before that, let's just go over some of these calculations. But there is a way that your gain does not degenerate, but still you get this benefit in terms of biasing. Yes. Exactly. You already know the solution, and the solution was shown in your homework 3. The bypass capacitor, that if you put a capacitor, and let me already talk about the solution because you guys know about it. So if you put a bypass capacitor over here, what would happen in that case is that in terms of DC, the capacitor is open because the impedance of a capacitor is how much? 1 over j omega c. That is the impedance of the capacitor. So at DC, when omega is 0, the impedance is infinitely large. So the capacitor is an open circuit. So in terms of DC analysis, the analysis that we just did will hold true. That if my VT increases, my current will reduce. If my current reduces, my source voltage will go down. If my source voltage goes down, my VGS goes up, and VGS minus VT remains constant. So the stability in terms of biasing is achieved because your capacitor is an open that does not affect anything. In terms of AC, the capacitance is a short. Let's say the frequency at which you want to operate, the capacitance is a short. And in that case, there will be no effect of this RS because the capacitor will already short the source to ground in terms of the AC frequency at which you're operating. And if the resistance gets shorted, your effective resistance is 0. So this GMRS term will become 0 and you'll get GM times VG. So you'll not get any degeneration if you use that bypass capacitor. That's the solution, exactly. That you use a bypass parallel capacitor to that resistor, you get the advantage in terms of biasing, but you do not have the disadvantage of source degeneration.
Do you consider that passive or high-pass filter? Like only for higher frequencies?
Exactly. And that's your that's a exam question actually, question number 3. That you had an input coupling capacitor, you have an output coupling capacitor, and you have a bypass capacitor for this source resistance in your exam question. And it is asked that, okay, what kind of filtering does it do? So of course, it will be a high-pass filter because at lower frequencies, of course, at lower frequencies, the capacitor is open, so it has no effect. At higher frequency, it shorts the source to the ground, so your gain improves. So of course, if you plot the gain with respect to frequency, the effect of having a capacitor over here will look something like this. Okay. That at zero frequency or at very low frequency, you will have the degeneration. But at higher frequencies, when the capacitor will short the source to ground. At higher frequencies, this effect of degeneration goes away, and then you get the full GM times VG. So this will be GM times whatever V in input voltage you'll have. And at lower frequencies, this would be GM divided by 1 plus GM RS. So at DC frequency, it will be this times V in. Or basically, if you, GM times, okay, if you're plotting the gain, then let me fix this. So GM times R out. And this will be GM divided by 1 plus GMRS times R out. So if you're plotting gain, when you do not have the degeneration, it's some GM times R out. And if you have degeneration, it's GM divided by 1 plus GMRS times R out. And in between, when the frequency changes, between the 2 points when the capacitor is considered as a open and the capacitor is considered as a short, in between that, you will have gain which is in between those 2 extreme points. So this looks like a high pass filter, right? So that basically says the effect of this capacitance is a high pass filter. Questions?
Do both happen in superposition? Like your biasing will exist at the same time as your AC input voltage?
Exactly. So if you consider DC, then your frequency is 0, right? And if your frequency is 0, you do not need to consider the capacitor. When you're doing AC analysis, your frequency is high enough so that, let's say you choose your capacitor in a way that at the frequency of your interest, the capacitor becomes a short. That's your job as a designer. And that was homework 3, right? Remember the problem given in homework 3? You wanted to find out the value of the capacitor so that the capacitor is a short at your frequency of interest. Right? So that's your job as a designer. And if you choose that capacitor value in a way that the capacitor becomes a short at the frequency of interest, so in terms of AC, it's exactly the opposite. In terms of AC, the resistance is not present and then you have a short to ground. Whereas in terms of DC, the capacitor is not present and you have a resistance to ground. So you achieve best of both worlds. In terms of DC, you have a stable DC biasing point. In terms of AC, you do not get the effect of the source degeneration that I'm showing here.
Yes. What's the difference between the small GM and the big GM?
Let me take that first. Please repeat the question on Zoom.
Sorry, yeah. What's the difference between the big GM and the small GM?
Okay. So the small GM is basically the transconductance of the transistor. Right? This is the transconductance of the transistor. So GM times VGS will be the current through the drain terminal of the transistor. Okay. The capital GM or the uppercase GM that I'm presenting here, that is the effective GM of the whole circuit. So this is the definition that what is the effective GM of the whole circuit? That the ID, the output current, the small change in output current divided by the small change in the input voltage of the whole circuit. So remember that this is just VG and this is not equal to VGS because there is a source resistance. And because of that, as you change the input voltage, the change in your output current will not be related directly with GM, but rather it will be related with GM divided by 1 plus GMRS. That's what we proved right now, right? So the uppercase GM represents the transconductance of the whole circuit, not just the MOSFET. Again, the concept is similar to the homework 3 problems, where the op-amp always has infinite input impedance, but the input impedance of the circuit could be something that is finite. Does that answer the question?
Yeah, that makes sense. Thank you.
All right, thanks. More question. GM is always AC. GM is always AC because GM is derivative of ID with respect to VGS. Whenever you're talking about derivatives, you're talking about small signals, small changes in the signal, right? Because GM is how do you del ID over del VGS? That's the definition of GM. GM for the transistor. So that's why I'm talking about, let's say, del VGS. But for the whole circuit, this will be derivative of ID with respect to derivative of the input voltage. In this case, the input voltage was VG, right? So input voltage to output current. Whatever relates that is the transconductance. Yes.
So that circuit on DC might actually have a +7 and -7.
Exactly.
We can't see that.
We cannot. We are not interested in that anymore because we are doing AC analysis now, and we're assuming that the DC analysis is already done and the transistor is in saturation. See, one other indication is that there is a ground over here. So that's an AC ground. That's not a DC ground because, of course, if it is a DC ground, there is no current flow from ground to ground. That there cannot be any current flow. So this is actually VDD, but VDD is also an AC ground. So now we are completely doing AC analysis. Assumption is that you have already biased the transistor in saturation, so the DC analysis has been done. Question? Mm-hmm. Yeah. Exactly. Exactly. So the superposition that you're talking about is the DC offset. On top of that, you have a AC signal, right? So you're analyzing the DC offset separately, that's homework 4, and you'll analyze your AC signal separately, that's homework 5. That's the basic difference. Yeah, but they happen at the same time. In a real circuit, both of them need to be there. If you haven't biased it, AC gain cannot be there. If you have biased it but haven't applied an input, you cannot expect a gain. You cannot expect an amplified output because you haven't applied an input, right?
And also, if you're big,
No. Let's not do that. I know that this could be a little confusing, but this uppercase GM, this is just the GM of the whole circuit. It's not talking about DC or AC anymore. GM is always, transconductance is always related to gain, because without that, there's no point of calculating transconductance. Right? So transconductance is always related to gain. I know that this could be a little confusing, so we might also want to use a different notation. But I want to differentiate the GM of the MOSFET from the GM of the whole circuit. That's the idea of representing this with uppercase GM. This does not talk about DC. Both of them are AC quantities. It's just that, again, we could have said something else. Let's say GM subscript whole circuit. Small GM, lowercase GM, subscript whole circuit. We can represent it at that as well. But this uppercase GM does not mean DC quantity in this case. It just means that the GM of the whole circuit. All right. So what did we find out? That the GM of the whole circuit is the GM of the MOSFET divided by 1 plus GMRS. That you have a degeneration in GM because of that source resistance RS. You can also represent that. So you can divide, again, something that we are very familiar with at this point, that let's say you divide all of that with GMRS. So your numerator will become 1 over RS, and your denominator will become 1 plus 1 over GMRS. So this is, interestingly, this is also very similar to the form of A infinity divided by 1 plus 1 over T. Right? That because your, what does it signify? Is that if your GM is infinitely large, if your lowercase GM is infinitely large, then this term will become 0. And what you'll be left with is just 1 over RS1. So if your GM of the MOSFET is infinitely large, the GM of the whole circuit is just going to be 1 over RS1. Right? So as you see that the GM of the whole circuit is not even dependent on the GM of the MOSFET in the limiting scenario. That if GM is infinitely large, you want a very high GM of the transistor because you want high gain. But even if the transistor has infinite GM, the GM, the uppercase GM or the GM of the whole circuit becomes just 1 over RS1. So that's why I wanted to draw this analogy with A infinity divided by 1 plus 1 over T, because A infinity talked about the gain of the circuit when the op amp is ideal. Let's say it has infinite gain and infinite impedance. Question? Yeah. Yeah, having a small GM of 0, of course, means that, because if the MOSFET does not have any transconductance, you cannot expect any transconductance of the circuit, right? Because MOSFET converts the voltage to a current. If that phenomena is not present, you cannot expect the input voltage to be converted to output voltage anyway. Okay. So bottom line, your GM got degenerated if you have a source resistance. But we also discussed that what is the way to get around it. If you have a bypass capacitor, then you can get back that gain in the AC. Let's take a look at a little bit more complex problem, but it basically talks about the same thing. Okay, so let's say this is your full circuit. Now let's see, your VDD is given to be 10 volts. Your ground, of course, is 0 volt. You have a AC voltage connected here, and that AC voltage is coupled using this AC coupling capacitor to the gate of the MOSFET. And the DC at the gate of the MOSFET is achieved using this RG1 and RG2. So this is kind of a mixture of your homework 4 problems and homework 5 problems. Right? You have both AC and DC. Right? You have the AC input over here, but you're also talking about the DC points because your VDD is given to be 10 volts. And from there, you can find out what is going to be the DC operating points. So of course, if this is 10 volts, this is 600 kilo ohms, and this is 400 kilo ohms, of course, you'll get a 6:4 division in voltages because the resistances are in the ratio of 600:400, so 6:4. So 10, if 10, this is 10 volt, the voltage over here is going to be 4 volts DC. So that's just the DC voltage of 4 volts. On top of the DC 4 volt, you are superimposing this AC potential, which is coupled using this capacitor C1. Now, of course, the capacitor is an open at zero frequency and it's a short at infinite frequency, which means that the capacitor and the resistors together, they are working as a high pass filter. So this is working as a high pass filter over here, the effect of that capacitance. Similarly, at the output side, you have another decoupling capacitance that also works as a high pass filter because it only gets shorted at higher frequencies. So high pass, so high frequencies will pass. Now your ID is given to be 1 milliampere. If ID is 1 milliampere and RD is 5 kilo ohm, so if the value of the drain resistance is given to be 5 kilo ohm, and the current, the DC current is 1 milliampere. So this DC current is 1 milliampere. That means that the voltage drop across RD is going to be 5 volts. So the drain voltage is going to be 5 volts. Again, DC, 5 volt DC. Okay. And if the current is 1 milliampere, if the source resistance is given to be 2.9 kilo ohm, so this is 2.9 kilo ohm. So you know that the source potential is going to be 2.9 volts, just Ohm's law. Voltage equal to current multiplied with resistance. So again, DC voltage at the source is 2.9 volt. DC voltage at the drain, 5 volts. So the DC VDS, the drain to source voltage in terms of DC, is 5 volt minus 2.9 volt. So that's 2.1 volts. Right? So let's just write that down. VDS is 2.1 volts. And that is just VD minus VS. So 5 volt minus 2.9 volt, that is 2.1 volts. Your gate voltage is 4 volts. Right? Your source voltage is 2.9 volts. So what is your VGS? VGS is going to be 1.1 volt. 4 volts minus 2.9 volt. So your VGS is going to be 1.1 volt. Your threshold voltage, or so now in the problem, either the threshold voltage might be given or the overdrive might be given. So both will signify the same thing eventually, because, or very similar ideas, because your VGS is 1.1 volt, overdrive is 0.25 volt. That means you can, overdrive is VGS minus VT. That means VT is equal to 0.85 volts basically. So the threshold voltage of the MOSFET is 0.85 volt. The overdrive is 0.25 volt. VDS is larger than the overdrive. That means the transistor is in saturation. And because the V overdrive is positive, the transistor is also on. It's not in cutoff. So your DC analysis is done, that the transistor is in saturation, and we know the value of all these parameters. Now, GM is given over here, but you could have also been given the value of K, right? K is mu n times COX times W over L. And if K is given, you know that GM is going to be K times VOV, which is just the derivative of the equation that ID is equal to K over 2 times V overdrive squared. If you take a derivative of that with respect to VGS, you get GM, and GM is equal to K times VOV. So your V overdrive is given. In the problem, in this case, GM is directly given to be 8 milliampere per volt. But it is also possible that in the problem, I give you the value of K, and then in that case, just multiply K with VOV, you get GM. Question? That's a small GM, lowercase GM, and that's basically the GM of the transistor. I'll never give the GM of the whole circuit. There's no point, because then there's nothing to solve. So the GM of the whole circuit is for you to solve, right?
And then if you have like
2 right, for each one. Yeah. So you solve for one stage and then solve for the second stage, right? We'll also discuss that probably in Monday's lecture. We may not get time today, but yeah, I'll always give the GM as the GM of the transistor, the lowercase GM, because the uppercase GM is for you to solve. That's the GM of the whole circuit. Okay. Now, if you talk about the AC equivalent circuit, the DC analysis was very simple. We just did it. Yeah, question. For DC analysis, we consider the capacitor as open circuit because 1 over j omega c is going to be infinite if omega is 0. That's DC. For AC analysis, you can consider the capacitor as a short because you would, of course, I mean, the value of capacitor is not given here, but that was your homework number 3, that you choose the capacitor in a way that it is a short at your frequency of interest. Exactly. So now in terms of AC, let's say you want to draw an AC equivalent circuit now. So what would be the AC equivalent circuit? Of course, the MOSFET needs to be represented with the small signal AC equivalent model. But even before doing that, what you can do is that you can short out these capacitors. So this capacitor is shorted, this capacitor is shorted, because now you're considering only AC. Your VDD is grounded, right? Because your VDD is an AC ground. So no need to consider that as a separate voltage source or anything. Because VDD is also an AC ground, your RG2 and RG1, they are in parallel in terms of AC. When you're doing the AC analysis, RG1 and RG2 are in parallel because both of them have this terminal as a common terminal, the gate terminal of the MOSFET as the common terminal, whereas the other terminal for both of them goes to ground. One of them is a DC ground, one of them is a DC VDD, but both of them are AC grounds. So your RG1 and RG2 are in parallel when you're doing AC analysis. Right? We're not doing DC analysis anymore. DC was very simple. We just figured out that the transistor is in saturation and that's it. For AC analysis, RG1 and RG2 are in parallel. Your RS is given to be, let's say, 40 kilo ohm or 10 kilo ohm, whatever the value. I think there is a mismatch here, but the value does not matter. Let's talk about the concept. All right. So what is going to be the parallel combination of RG1 and RG2? RG1 was given to be, let's say, 600 kilo ohm. RG2 is 400 kilo ohm. So parallel combination is 600 multiplied with 400 divided by 600 plus 400. And that will give you 240 kilo ohm. So this resistance over here is 240 kilo ohm, the parallel resistance of the two. Yes. That's the yeah. So if you are, let's say, okay, let's clarify that a little bit. So if you are talking about Rin as the resistance looking here, then yes, that's the total Rin, right? Because that's the resistance you see to ground. And then this side, you see a MOSFET's gate, which is an infinite resistance anyway. So that's your Rin for this circuit. All right. Now, RD is given to be 5 kilo ohm, RS is given to be 2.9 kilo ohm, and GM is given as 8 milliampere per volt. Now, because you have a source degeneration, what is going to be your uppercase GM? What is the overall GM of the circuit? That's going to be GM divided by 1 plus GM RS1. You can also do the entire small signal model based analysis and figure out, but it will be the same thing that if you have the source resistance for the MOSFET, the GM for that configuration that you have a MOSFET with a source degeneration, the overall GM of that circuit is going to be GM divided by 1 plus GM RS1, where you are trying to convert the voltage present at the gate. So let's say voltage present at this point to a current that flows through the drain. And this uppercase GM will create the relation between the voltage present at the gate of the MOSFET and the current that flows through the drain of the MOSFET. In the scenario where you have a source degeneration resistance connected to ground. Okay, that's what we learned, right? So GM is going to be GM divided by 1 plus GM RS1. Now you can calculate that because all the values are given. GM is 8 milliampere per volt. Your RS is 2.9 kilo ohms. So you calculate that, you find out that your GM becomes 0.33 milliampere per volt. That is the effective GM. That's a very low number. I mean, as compared to 8 milliampere per volt, you have degenerated, the GM has been degenerated to 0.33 milliampere per volt. Also, that is very close to 1 over RS1. So remember, we said that if GM is infinite, this equation boils down to 1 over RS1, right? If GM is infinite, let's divide the numerator and denominator with GM. You get 1 over here, you get 1 over GM here, and then you just have RS1. If GM is infinitely large, this term also goes away. What you're left with is just 1 over RS1. So in this case, GM is not infinitely large, it's 8 milliampere per volt. But even in that case, your 1 over RS1 would have been 1 over 2.9 kilo ohms, that is 0.345 milliampere per volt. So there's not a whole lot of difference. See, that if you just calculate 1 over RS1, you get 0.345. If you calculate GM divided by 1 plus GM over RS1, you get 0.33. And that's why I say that in many cases, in electronic circuit, it makes sense to do that little bit of approximation, because otherwise your equations will be too complex. But if you understand the problem well, then you can do a lot of approximations, which will make your life much easier. So 1 over RS1 or GM divided by 1 plus GM RS1 will be almost similar, because GM is quite large as compared to, originally this lowercase gm was quite large as compared to 1 over RS1. And that is the reason why these two values are very similar to each other. All right, so that's just uppercase GM. Question? Yeah. Right. And if it had been infinite, then they would have been exactly equal. This equation and that equation is exactly equal if GM is infinite. In this case, GM is not infinite, but GM is much larger than 1 over RS1, because 1 over RS1 is 0.3, whereas GM was 8. So that's like a 30 times difference, right? So on the other hand, if the difference was, let's say, 2 times, let's say 1 over RS1 is equal to 1 and GM is given to be 2. If the 1 over RS1 and GM, they are very close to each other, then you cannot make that approximation. Right? Only reason you can make this approximation because GM is much larger than your RS1, 1 over RS1. And that's why even with this approximation, the values are very similar to each other. So when you're solving a problem, be careful of the fact that whether your approximation makes sense or not. Approximation is always allowed in electronic circuit, but you just have to make sure that you know whether it makes sense or not. In this case, it will make, if GM is, let's say, 10 times larger than 1 over RS1, it will make sense. If GM is 2 times larger than 1 over RS1, approximating it to 1 over RS1 does not make sense. Okay, all right. So we found out uppercase GM. To find out gain, you need the uppercase GM and you need the equivalent resistance at the output, right? GM multiplied with R out will give you the gain. So we just found out GM. We still need to find out R out, output resistance. Where is the output? The output is over here. So looking at this terminal, what is the total resistance that is connected? Of course, looking down, you'll see the resistance of the MOSFET. Looking up, you'll see RD. And of course, at the same node, you'll have a RL resistance connected, which is 20 kilo ohms. Now, if you consider that the MOSFET has a finite lambda, that is the channel length modulation parameter, then you need to actually calculate how much resistance do you see looking into this drain node of the MOSFET and so on. But if the channel length modulation parameter lambda is assumed to be 0, then the MOSFET's RO, the output resistance of the MOSFET is going to be infinitely large. So the resistance looking into the drain of the MOSFET will be infinitely large if lambda is 0. The channel length modulation parameter is 0, and what will happen in that case? The ID versus VDS characteristic will look exactly parallel to the x-axis. So this was your VDS, this was your ID. If ID is exactly parallel to the x-axis, that means that the resistance in this region is infinitely large, right? Because if you make any change in VDS, current does not change. That means resistance is infinite. So if it is an ideal MOSFET with lambda equal to 0, the resistance looking down on this drain terminal is going to be infinite. So you don't need to consider that. What are the other resistances that remain? The resistance looking up is basically RD, and resistance over here, because this is also connected to ground, right, at this point, this RL. So the resistances that are connected to the output terminal are basically the RD in parallel with RL. Why are they in parallel? Again, because VDD is also an AC ground. So RL equivalent is RD in parallel with RL. So you have 5K multiplied in parallel with 20K, that's going to be 4K. So what's going to be your GM times RL equivalent? And remember that here, the gain that we're talking about is just V out divided by whatever voltage you had at VG. Why is that? Because we started with GM. And GM gives you the relation between the voltage that is present at the gate of the MOSFET to the current that is flowing at the drain of the MOSFET. So anything that had happened before the gate of the MOSFET had not even been considered in this uppercase GM. So GM is only considering the point that the gate of the MOSFET is, you get some voltage at the gate of the MOSFET, and after that the MOSFET converts it to current, and then you multiply that with the output resistance, you get the output voltage. So this voltage gain, VO over VG, that's going to be GM times R equivalent. That is just 0.0345 multiplied with 4K. That gives you minus 1.32. But that's just the gain from the gate of the MOSFET to the output of the MOSFET. It's not the gain from the input voltage source to the final output voltage. Again, you have solved similar problems in homework 1, 2, and 3. So what do? You just calculate the voltage division at this point, right? Between the source resistance RS of VS and then the input resistance of the circuit, which is 240 kilo ohm. So you calculate that, 240 divided by 240 plus 40, that's the additional voltage division ratio. That multiplied with 1.32 will actually give you the overall voltage gain of this full circuit, and that is going to be minus 1.1 or something. Okay? So it's just basically a voltage division that happens between these resistances multiplied with the voltage gain that you have calculated over here. So let's stop here and we'll discuss about more problems in Monday's lecture.